doing. So I realized that on Wednesday, in the end of the lecture, I've been talking again too fast, so I decided to repeat a couple of questions related to transformers. So let's start from this situation. We know that for a regular transformer to work, we connect it to a source of AC, alternating current. In the primary coil, voltage constantly changes. It generates constantly changing magnetic field. That generates constantly changing EMF in the secondary coil. But what if, instead of using a generator, we use a battery connected to a primary coil, like in this example? What do you think is going to be happening with the current in a secondary coil? So as long as we close the switch, we'll see your the answer in a minute. But first, let's actually try out this experiment. So I have two coils. It always pops up. What was number 2? Constant and equal. Okay, we'll see in a minute. Kind of dark. So, this is supposed to be a primary coil, that's supposed to be a secondary coil. The secondary connects to a galvanometer. So, if any current will be generated in the secondary coil, you're going to have to see it here. The best we can get. And I don't have a switch. Instead, I just connect this battery directly to the primary coil. And now, so what is happening when I close the switch, when I open the switch? Closing the switch. You see? Arm moves away from equilibrium. However, after that, it doesn't stay in that position. It goes back. So there is no current anymore. When I open the switch, we observe the same kind of behavior. Why is it happening? Why it doesn't stay? Well, the answer is simple. We don't connect the battery directly to the galvanometer. We connect it to the primary coil. So, and when I close the switch, come on. So, when I close the switch, now in the primary coil we have a constant current, not AC, DC. The current doesn't change here. So in a moment when this switch has been closed, of course the current goes up from 0 to some final value, and magnetic field in a coil, of course, goes from 0 to some final value, and the flux does the same thing. So the flux changes, and during that time interval, when the flux changes in a primary coil, it also does change in the secondary coil. But after that, when the current in the primary coil reaches its maximum value, the flux reaches its maximum value in both coils. And after that, the flux doesn't change anymore. No change, no induced EMF, no induced EMF, no induced current. So the current spikes and goes back to 0 again. Well, what do you think is going to happen now? I'm going to start a timer and prepare this setup for this question. It's very simple. Yeah, we know how to make a person land on the moon. We don't know how a person thinks. We have no idea why we choose, some of the possible answers. But what we do know in physics, we always can check. So here, again, now. This is the primary coil, and the battery is just connected to it, so it runs the current constantly. But there is, of course, a flux generated by a magnetic field through the coil, and that's a secondary coil. All I have to do now, I again don't have a switch, I just can connect this wire and see if anything happens. Nothing. Well, why would this coil, the secondary coil now, is not a battery. It doesn't have any potential difference across its terminals. In order to have potential difference, the flux through this coil has to be different at different times. It has to change. But the flux provided by the primary coil is constant. So constant flux, it doesn't matter if you have it connected or disconnected. It doesn't affect this galvanometer. It doesn't generate any current inside it. All right, so if you answer correctly, you can say good things to yourself. If you answer incorrectly, don't say anything. And the last thing, we use transformers a lot, every device. If you remember, it's been a question about capacitors. Your cell phones or computers have capacitors, and your cell phones also, and computers and TVs have transformers inside, because this is a way you can manage, well, the voltage and the current. And one of the application of transformers is transporting the electricity from a power plant to everyone's home. Basically, the idea is simple. The problem with transporting electricity is that, it's going to be even worse in a recent, brief future, close future. Well, you know that the power dissipated by current is proportional to current squared, I squared times R. So the higher current is, the more power gets dissipated in wires, the hotter they become. So imagine, if you had transport electricity along a long line with a, the longer line is, the higher resistance. So we would lose a lot of energy. We would be heating air around it. So to prevent this from happening, what we're trying to do, we're trying to increase the voltage. When we're increasing the voltage, we're decreasing the current. So that's why we have first really powerful step-up transformers close to each power plant. The voltage goes up to 100,000 volts, but the current goes significantly down. And then we use a set of step-down transformers, and eventually, after actually a series of step-down transformers, we get this voltage 120 volts. That's how we use it. Any questions on Faraday's law, Lenz's law? Well, we're going to have, after the spring break, of course, a review session before the second test. But if you have questions now, let's talk about it. If not, we're going to have to start a new topic. And it's a big event because finally we get back to the syllabus. That's what we're supposed to talk about today. Waves. So there is no snow day anymore. It's done. It's done. Wave. Well, everybody's seen a wave at least once on the surface of water, or you can attach a rope, to the doorknob and wave another end. And that's how it looks like in general. This is one kind of wave. It's a set of ups and downs. Each wave basically is a set of pulses. So I can just make one pulse, and this pulse is traveling along a string or spring. And if I keep generating pulses, those pulses travel one after another, and they form a wave. And first of all, of course, if I shake it really fast, that changes how close pulses to each other. Or if I make a really large motion, it gives a large displacement from the equilibrium. So there are several parameters we have to use to describe a wave. And different pulses might travel with different speeds. So different waves could be also described in terms of velocities. Most important part about wave, any wave, it always represents some kind of a displacement from some kind of equilibrium. Electromagnetic wave, light wave, sound wave, mechanical wave. So it's some kind of disturbance. Wave, well, except electromagnetic wave. All mechanical waves require some medium, like air or water or rail. And we have to disturb the state of the medium, and that disturbance might be traveling away. That's what we call a wave. What's important is that, well, we have two kinds of waves. This is another kind. Not sure if you will be able to see it, but try. I can make a pulse again. Series of pulses. Basically what is happening here, when this slinky is not disturbed, the average distance is the same between all adjacent loops. And when I start changing the distance, series of pulses travels away, and at some point we have well, density of slinky goes down, and sometimes it goes up and down, up and down, up and down, and that's what comprises the wave. But the difference between this wave and that wave on a string is that here, all the particles of this string move up and down. And that's how I was waving. When I make a pulse, I move my hand in vertical direction, but pulses travel horizontally. So the angle between the motion of each individual part of the string and the velocity of the wave is 90 degrees. That's one situation. Another situation is happening here. Here, each individual part of this loop moves horizontally, and pulses travel horizontally in the same direction. So because of that, we have two kinds of waves. The waves of the first kind, when particles move perpendicularly to velocity of the wave, we call transverse waves. And the waves of the second kind, when particles of the medium move in the same direction as the wave propagates, we call longitudinal waves. And sound waves, for example, are longitudinal waves. Well, this picture is supposed to represent how atoms of the air move when we speak, for example. So again, at some points, atoms close to each other, density is higher than the average density, and at some points, the density of the air is lower than the average density. And that's how sound waves look like if you could see it inside. Transverse. What's important to understand that when we generate a wave, we are the source of the energy. We are pumping the energy into the wave, and that energy transfers or travels away. Why? Well, because we push on the part of the medium close to our hand. Those parts push on the next and the next and the next and the next, and the energy which we are pumping in the wave travels away. Well, in all directions or in a specific direction. However, you do not see that the slinky was moving. No. So there is no transport of mass in a wave. If you look at a single point of a wave, it doesn't move to the left, it doesn't move to the right. It just moves about the equilibrium position. So the wave doesn't move as a whole object in one direction. It just keeps moving elements nearby. And the same is true for longitudinal waves. Again, even if we observe a certain horizontal motion, on average, these particles stay at the same location. There is no transport of mass, but energy from the source getting transmitted, transported everywhere. Well, I have one more picture. More density of particles. Density or medium. Transverse, longitudinal, again, we don't observe any transport of the mass. What else do we have? More points to look at. You see? They all keep the same location. And actually, even mathematically, the description for transverse waves and longitudinal waves is absolutely equal, it's much easier, well, when we solve problem related to wave, it's much easier to use transversal representation. It's just easier, you just draw a wave like that, and that's it. Now, if we look at a single particle, it moves up or down like this, or like this. This is a well-known motion you've studied in previous course. Well, how do we call it? We call it, how do we call it? The motion like that. Simple harmonic motion, right. So you know everything about this. Well, the simple harmonic motion, the standard equation which describes it, involves a harmonic function, cosine or sine, usually cosine. And what we know is that if you want to describe this motion, usually we introduce a variable which describes displacement from equilibrium. This variable. That displacement always has some maximum value, and it takes a specific time interval, a specific amount of time to make one whole motion. We call it a period. The period is related to frequency. Frequency says how many oscillations happening per second. And we also sometimes use this variable which we call angular frequency. Basically it says how many oscillations happening over 2 pi seconds. And all these variables are related, nothing new. What is the difference between simple harmonic motion and a wave? Is that in a wave, simple harmonic motion happens simultaneously at different locations. That's it. So for each particle of a wave, we can apply the same equation. And of course, some of these variables are supposed to be all the same for all parts of a wave. But not all of them can be the same, otherwise that wouldn't be a wave. Otherwise that would be the whole rope or string moving up and down, not like this. So it's supposed to be something different. So this is my first question about the wave. What do you think all those points have in common? You look at the wave like this. All parts of this wave make harmonic motion. Well, this is a very special wave. We're going to study the property of this wave after the break, but still it's a wave. And you can look and compare, for example, amplitudes, periods, frequencies for two different points, for two different particles. Well, I probably should have asked what they don't have in common. What's the difference? Well, all parameters cannot be the same. Again, if all parameters would be the same, that means they all would be moving absolutely identically. It would not be a wave. So, but there is one parameter which differs. This one. They all have the same maximum displacement from equilibrium. They all have the same A, amplitude. And they all have the same period. They all make one whole motion during the same time interval. So same period, same frequency, same angular frequency. But something's supposed to be different. If not A and omega, it's supposed to be this. So this parameter is different for different parts of the wave. How different? Well, since any wave is just a set of traveling pulses, if we know what is happening to one pulse, we know everything about any kind of wave. So imagine you made a pulse at the origin, and that pulse is traveling away. Well, of course, in real life, there is some friction and the pulse kind of eventually dies out, but we disregard any friction. So we know that this pulse just keeps its shape. As long as the spring doesn't end, this pulse is traveling, keeping the same shape, same amplitude. And so if you wait a certain time, this pulse will be a certain specific distance away from the origin. Distance is equal to velocity times time, that's it. So this is the picture for initial situation, and this is after delta t seconds. Now, the displacement from the equilibrium, this function, here should be equal to the displacement from the equilibrium there. It's the same shape, same value of y. So what we say is that displacement here and now should be equal to displacement at the origin this time ago, when it was at the origin. That's it. And all we have to do just now, rewrite this mathematically. So, well, for our wave, not just single pulse, for a set of pulses, if at the origin we wave it up and down, and this function describes the displacement from the equilibrium at the origin, in that case, the displacement from the equilibrium here is supposed to be described by the same function, but we just have to shift the time back. And since time, velocity, distance related, now we can just simplify this expression and rewrite it in terms of distance. Time is the distance over velocity. And, well, normally we would like to simplify. So this expression, this fraction, minus x omega over v, that would represent this little pipe, which is different for different points. How different? This how different. At different x's, this value is different. That's it. You go at x equals 1, that gives you one number. You go at x equals 2, that gives you a different number. So, but amplitude and angular frequency is the same everywhere. And we just usually introduce a new variable. We don't like fractions, so we get rid of fractions. We introduce a new variable, and we call it a wave number, or sometimes wave vector. And now if we use this variable, which could be calculated in different ways, our function looks very easy. No fractions at all. So we can calculate, if we know amplitude, angular frequency, and wave function, and wave number, we can calculate the displacement from the equilibrium at any time, at any place. So for the wave, we have to use two variables. For a simple harmonic motion, we use only time. For a wave, to describe the wave, we use time and position, t and x. Well, and let's look at these two pictures. The top picture represents an actual wave. We see it. Look at the spring. So the top picture we call a photograph, a snapshot. That's what we see. The bottom picture represents the motion of a single point. This point moves up and down, up and down. So in the top picture, we have two axes involved: y, displacement from equilibrium, and x, a ruler. Here we use two variables, but different ones. Y, the displacement from the equilibrium, and t, time. This graph represents the displacement of this point as a function of time. This photograph represents the shape of a wave at specific instant. And if you look at the photograph, displacement as a function of distance, photograph can be used to introduce a new variable, the shortest distance between any 2 points moving in phase. We call it a wavelength. And the graph, displacement as a function of time, gives a way to calculate the period, how much time, the shortest time, to repeat the same motion. So, how would we answer this question? If a certain point on the wave makes 30 oscillations per minute, what is the period of this motion? What is the frequency? What is the distance does a single point travel if the amplitude is 1 millimeter? So, let's do it together. Oscillations per minute. Oscillations, 30 times 2 seconds, 60 seconds, 1 minute. So to calculate the period, T, what do we do? Or, that's my question to you. If you think this is the correct way to calculate the period, press 1. If you think this is the correct way to calculate the period, press please 2. The period is a time. It's a specific time. It tells how much do we have to wait until the particle again goes back to its initial position. So first of all, this fraction doesn't have a right unit. A unit for this expression is 1/2. A unit for the period would be second. So if we know how much time it takes a certain amount of motions, we take that time divided by the number of oscillations, that gives the period. So in our situation, the period equals 2 seconds. 60 seconds divided by 30. So it takes 2 seconds for each particle of a wave to get back to original position. Usually, we start from equilibrium, so from equilibrium it goes up, back to equilibrium, down, back to equilibrium. That's one whole motion. It takes 2 seconds. And now we know that the amplitude of this motion is 1 millimeter? Yes. So it goes up, down, even lower down and back. This is one whole motion. It takes 2 seconds here to make it. And if we wait, how long do we wait? Well, let's say 1 minute. If we wait 1 minute, and if the amplitude is 1 millimeter, what is the distance traveled by this particle? Total distance traveled by this particle. All right. Please, tell me your number. It doesn't have to always be a multiple choice question. You can just calculate it and tell me your answer. Well, when it travels up, then back to equilibrium, then down and back to equilibrium, when it makes one whole motion, it travels 4 millimeters. But we have to wait 1 minute, and we have to calculate total distance traveled by a particle over a minute. So, it travels 4 millimeters when it makes one oscillation. How many oscillations does it make over a minute? I think you already have an answer, right? Not yet? All right. So how many oscillations does it make? If we wait 1 minute, so how many times it oscillates? Anyone? The period is 2 seconds. The period is 2 seconds. If we wait 1 minute, how many periods does it fit? 30. So, if we wait 1 minute, well, remember our expression for the period. We just now use it differently. Now we are calculating the number of total oscillations, which is the total time divided by a single period. Well, of course, we have to use the same unit. So 60 seconds over 2 seconds, 30. What number actually was given to us? So it makes 30 complete oscillations, and one complete oscillation gives 4 millimeters of traveling. 1, 1, 1, 1. 4 millimeters for one complete motion. So what is the total distance traveled? 4 times 30. 120 millimeters. 1 meter, 20 centimeters. Any question? So this is a simple, actually review question. It doesn't relate it yet to a wave per se. So far we talked about the motion of a single particle of that wave. Well, as you know now, we always can use 2 representations. We can use a photograph. It's an actual wave, an actual rope or spring. And we can use a graph. If we want to calculate the wavelength or find the wavelength, what would we use? Well, we don't need this graph for the wavelength. We need for the photograph for the wavelength. The wavelength what related to how wave is spread, in the space. So we just look at the distance between 2 nearest bumps, and that's the wavelength. If we want to find the period, now we have to relate the motion with time. So now we have to use a photograph, a graph. Now, there are 2 different velocities related to a wave. One is how fast each pulse is traveling. This velocity depends on the properties of the medium. Spring, string, wire, or sound, or, well, in the air, or sound in liquid. For each situation like that, we have to use different expressions to calculate the speed of the wave. If we have a string, like guitar string, for example, this is how we can calculate how fast it's traveling. We just need to know the tension, and we can change it in the string. We need to know the density. Well, it's a mass divided by the length. And of course, that speed, the wave speed, is related to the distance traveled over time. How can we calculate that speed? So it takes exactly one period to travel exactly one wavelength. So the wavelength divided by the period equals the speed of the wave. So we have two expressions for this wave velocity, wave speed. This is number one, this is number two. We'll actually have more, for example, for the speed in the gas, in the air, for example, or for the speed in a solid. Yeah. So we could use any of those expressions. However, in any situation, we always can use the relationship between the wavelength, period, and the wave velocity. Now, this is a different situation. This particle is moving up and down. So the velocity actually changes over time. It reaches zero when it reaches maximum displacement. Then it's speeding up. The velocity is at its maximum at the equilibrium position, but then it slows down. It's a simple harmonic motion. So this is how fast pulses travel, the wave velocity. And this is the velocity of a single particle in a wave. What do you think about these two velocities? Are they equal to each other? So, yes, they are equal to each other. No, they're not. Or the question kind of is ambiguous, and it might depend on the nature of a wave. What do you think? 13 seconds. On a clock, like a Jeopardy. Only without mine. Well, I suppose you answered yes because of my bad English. Because I tried to tell you the answer. This velocity changes. This is not. So they just can't be the same. Wave velocity is a fixed number. It travels, well, sound travels at 330 meters per second, for example. But the particle moves at different velocities at different times. So these are two different velocities. And it's very important to understand the difference, because sometimes you read a problem, it says find velocity, and you're calculating a different velocity. Okay. How would we get that velocity? Very simple. Again, to calculate the maximum velocity for each individual particle, we don't need any new expression. We just have to recollect what we've studied in PY105. For a simple harmonic motion, well, if this is the amplitude of displacement as a function of time, this is the angular velocity. Angular velocity or angular frequency is one thing, and velocity is a different thing. So angular frequency, to calculate the maximum speed of the particle motion, we just have to multiply these two variables. Again, you can use analogy, a recent analogy. Remember a generator, when a loop rotates, the EMF changes over time. To calculate the maximum EMF, you had to multiply some variables and angular frequency as well. So very close analogy. I'm going to ask you this question. Basically, since we have so many variables, they're all related to each other. So for example, for calculating wave velocity, we could use so many different expressions. Which to use depends on the problem. And this is one possible problem. Yeah. You just want to calculate the wavelength of a radio wave. What do you need to know? Speed and frequency. And you know the numbers. You just plug the numbers. Turns out that Well, wavelength for a radio wave is a rather reasonable, like meter, 2 meters, 3 meters. For light, it's completely different. For sound, it's close to this. Now, what's important? That remember the equation we wrote for the wave. It looked like that. We had it derived for a wave traveling to the right. My picture was here, pulse was here, then here, the motion to the right. What do we change if the wave travels to the left? Well, it must have the same amplitude as the same wave. The amplitude depends on the source. That's it. The frequency depends on the source. The wavelength depends on the medium, how dense it is, and frequency. So we cannot change neither of these variables. This only what we can change. So when the wave is traveling in opposite direction, we just have to replace a minus with the plus. Traveling to the right, minus. Traveling to the left, use plus. To the left, use plus. And this is one of a standard situation. Let's say you are given a specific equation. So how much information you can extract? A lot. Whatever you see right in front of sine or cosine is the amplitude, the maximum displacement from equilibrium. So we immediately get the amplitude. This number right in front of time is the angular frequency, so we just rewrite it, angular frequency. This number near the x variable, that's the wave number. So as long as we know these numbers, we can now apply all our expressions to calculate whatever we want to calculate. For example, we can calculate the wavelength. We can calculate the regular frequency. We can calculate the period. We can calculate, well, the period is 1 over the frequency. Now, if in addition, let's say, well, we can calculate the speed, it's just frequency times wavelength. If in addition to these variables, we know the density, we can use this expression and to calculate the tension in the string, for example. Well, and we also can calculate another speed, the speed of a single particle. So this is the wave velocity, 4.2. This is the speed of the single particle, 4.5. Again, we can see different variables. Well, meters, centimeter. So very different values for different speeds. Well, you say 50. We are done for a week.